We're going to continue talking about numerical differentiation. In the previous lecture, what we talked about is how we can use Taylor series expansions to approximate the slope of a line, essentially being the derivative, and using what are called finite difference techniques. And by using more and more neighbors, we can produce more and more accurate representations of the derivative. Importantly, a lot of the error estimates that we had were constrained by some either delta t squared accurate or delta t fourth accurate type approximation of the derivative, where delta t was the step between points. And of course, one has led to this idea that, oh, all I have to do is make delta t smaller and smaller and smaller to gain more accuracy. And although this is largely true, there is a limit. In fact, numerical round-off in your computer system actually limits how small a delta t you can take before, in fact, your error starts to increase. So we're going to talk about this other aspect of computing derivatives, which is how does numerical round-off actually play a role in limiting how well you can compute a derivative. Okay? So we're going to go after this still, numerical differentiation techniques, and we're going to see how do we do this and how do we start to account for numerical round-off. All right, so round-off and step size. So first of all, your computer typically has something like 16 decimal place precision. Of course, there's a lot of architectures now that allow more flexibility of how to represent floating point operations and floating point numbers, but we're going to go ahead and assume that typically 16 decimal place precision is going to be sort of a standard double precision mathematical computing. And so what we're showing here is when you actually ask your computer to compute a quantity, it does so, but up to numerical round-off. So if I want to compute the key components of what would be a numerical differentiation scheme, then I'd say, okay, y of t plus delta t. So that is the estimate of y, at delta t. And remember, I'm going to use this in my slope formula. Well, what it actually is, in the computer, it's represented as capital Y. In other words, there's a numerical representation in the computer. Let's call that capital Y. And this epsilon here represents the numerical round-off. So no number is really represented completely. It's only represented to 16 decimal places. And that actually plays a role in limiting how accurate we can make these derivative estimates. And I'm going to show you this explicitly. Likewise, if I represent y of t minus delta t, which is the other component, remember in my compute slope formulas, I'm using neighbors. So this is my other neighbor. It has a representation, capital Y t minus delta t, with numerical round-off epsilon. So both of these, when I compute them in actuality on a computer, which I have here, they're going to be finite representations to 16 decimal place accuracy. So what are the implications of that? Because normally we don't think about that so much. We think, okay, fine, I just can compute things. I don't have to think about numerical round-off. But when you're computing derivatives, and you're trying to actually get more and more accurate derivatives, numerical round-off most certainly plays a role in limiting your capabilities of producing derivative estimates. So let's compute the error estimate. Remember that when we do a computation, here is an order delta t squared numerical differentiation scheme that we learned in the last lecture for computing the first derivative. It's a slope formula. It's rise over run. This point in front, t plus delta t, minus point behind, y of t minus delta t, and the run is 2 delta t. So this is a simple slope formula, and if you remember, this produced an order delta t squared accurate representation of the slope. But now when I actually go to compute this, what I'm actually getting for the values is the numerical value that would be produced in the computer minus the numerical value of this in the computer. And what I'm representing here, this E, it's the error that's involved now in approximating the derivative. And the error is going to come in two forms. First, there is the Taylor series expansion that I cut off, right? The delta t squared term that I have. But now we're introducing this other term here, which is the numerical round-off. So the numerical round-off that comes, which is in 15th, 16th decimal place, is now sitting over here. As I approximate this, it actually gives me an error contribution to the estimate of the derivative. So here is it more precisely. My error is the round-off error plus the Taylor series truncation error. And the numerical error for the round-off is given by these epsilons, these numerical 10 to the minus 16th, 10 to the minus 15th estimates of the derivatives. And then here, this delta t squared, this is the Taylor series expansion cutoff that I had from previously. Okay, so my error isn't just the Taylor series expansion cutoff, it's now this numerical round-off error where I only have a capability to approximate any number down to 16 decimal places. So let's try to estimate how big this error can be. So we're going to estimate this by saying, look, the error, the absolute value of this round off, let's say, is bounded by, let's call it epsilon r. So epsilon r being the machine epsilon round off error. Okay? So I'll bound both the estimate of the point in front and the point behind by this, right? Because those are the estimates of the slope are based upon point in front, point behind. And then I'm also going to say, well, you know, computing this third derivative, let's just say that it has a max value m. So what I have here is, in some sense, the biggest values these things can be. And I'm going to put that then, that's going to bound how big my error can be. In fact, if I put these into the formula I just had previously, which had the round-off error plus the Taylor series expansion error, which is right here. So the error now is bounded by, I put in the biggest values they can be. So I have a round-off error, which can be size epsilon r for both the estimate of the front term and the back term, plus if the derivative is maximum size m, this here tells me the total maximum size of my error. I can combine these two terms together, so it's going to reduce in this formula here. So epsilon over delta t plus delta t squared, maximum size of the derivative. Now, right away, you see a kind of an interesting issue here. The numerical round-off produces a 1 over delta t. So as delta t goes to 0, that term is going to infinity. Whereas delta t squared goes to 0 here, this goes to 0. So notice, though, that the combination is important. So if the delta t is big, this error grows, the Taylor series expansion truncation. If delta t is small, the numerical round-off takes off in terms of making a problem with the error. So this is a trade-off you have to balance. In fact, you can ask the question, where is the minimum error? Really simple to compute. Take the derivative of that error with respect to delta t. And what you end up with is this formula right here, and you set it to 0, which allows you then, okay, so we just took the derivative of the error. This is it. We set it to 0 at where this is 0, wherever the delta t is 0. That's going to give us the max, where the error is minimized. And that error is minimized because what we have here is as delta t gets small, we have a 1 over delta t growth. As delta t gets big, it grows like delta t squared. And so you can already see somewhere in here is my minimum error, which we can compute by taking this derivative. And this is where it is here. So this here gives us the smallest delta t we'd ever want to take, because if we take delta t smaller than this, numerical round-off is going to take off on us. So let's actually just estimate this. E of r is here. We'll just say m is 1. E of r is the big thing. That's the numerical round-off. And typically, numerical estimates are around 10 to the minus 15, 10 to the minus 16 accurate. So let's go ahead and take 10 to the minus 15. So if this is 10 to the minus 15, it's raised to the 1/3 power. So this here becomes 10 to the minus 5. So you would never want to take, for this scheme, a delta t that's smaller than 10 to the minus 5. In other words, you can't just simply push delta t towards 0, make it smaller and smaller and smaller, because once you get below 10 to the minus 5, now numerical round-off, your error is going to start going back up simply due to numerical round-off. So that's an important thing to keep in mind, because that limits, ultimately, the error. Right? You have an error floor. No matter how you compute this, you're going to get an error in the derivative estimate, and you can't just simply make delta t smaller to make it go away, because numerical round-off takes off. And again, this is sort of the break-even point there where you can push it down. So this is an important feature of numerical computing. You should always understand you're dealing with finite differences, finite number of points. You're using Taylor series approximations, and it's not just simply about the delta t. It's also about the fact that computations are represented with finite size numbers and finite precision, and these all play a role in your ability to compute and accurately compute estimates such as like the derivative, which is what we've been focusing on. I want to work into a Python code now because these algorithms are actually quite simple in many ways, right? They're really simple to write. And so I want to write a little finite difference code, which is right here. And so what I'm going to do is give you a little, there's my dx. This is going to be my finite difference, right? And this dx here, oops, go back. It's 0.01. And then I'm going to make an x variable. This is going to be my x range. And I'm going to make the function sine of x, okay? So this is my whole code here. So I'm going to differentiate sine of x. So I make sine of x. By the way, we know what the exact answer is. It's supposed to be a cosine. So if I differentiate sine, I get a cosine. So I'm going to take this and I'm going to numerically differentiate y over the interval x. And I can compare it directly to the known answer, which is the cosine. So it's a good sort of, say, sanity check. In fact, anytime you're coding, the first thing you should always do in coding is make sure you can solve a problem you know the answer to. Always. Because you'll right away understand if your code doesn't work when you try to get the answer and you can't even get the answer you know the answer to. Okay? So that's an important coding tip. So here's what we're going to do. We're going to make a vector of zeros. And what you see here are the forward and backward difference formulas. So first of all, y of p is going to be my derivative, okay? And remember, I'm using a center difference formula. So the center difference formula relies on its two neighbors. However, when you're at endpoints, I don't have two neighbors. I don't have a neighbor on the left and right. If you're on the left point, you only have neighbors to the right. And if you're on the right point, you have neighbors to the left. So what this is doing is saying, okay, if I'm on the left point, only use the neighbors to the right, and that's in that finite difference formula table. If I'm on the right point, use two neighbors on the left. And so now I can compute the two derivative estimates, and for everybody else, use the finite difference formula, which is the rise over the run. 1 point in front, 1 point behind, divide by 2 delta t. Or in this case, delta x. That's as simple as it is. This here is a finite difference scheme executed in Python. You have the script in your code. And this is just basically programming the first line of one of those differentiation tables, and that's as simple as it gets, okay? So this is how you would actually build derivative estimates, and it's and you can see that finite differences are just going to be loops through all the variables, through all the different points, use the neighbors, compute derivatives, and of course, if you want more accurate derivative estimates, you can use the delta t to the fourth schemes that are on the table. They're as simple as what I just showed you there in Python. You can write these in Python very nicely, and it will give you the ability then to estimate derivatives given a data set that you might play with, or it could be that you use these to estimate derivatives and then solve differential equations or partial differential equations with them.